All right, everybody, welcome back to the Physics and Astronomy session. Here we'll be hearing about AI as a detector, Pulsar detection from Adam Thompson from NVIDIA and Luigi Cruz from the SETI Institute. So, please, take it away.
Thank you, Jim. Thanks, everyone, for attending this talk. SciPy has been and has a special place in my heart over the years. It's just really amazing to have the opportunity to speak with you because it's all these great minds that are solving really challenging problems together and writing amazing software packages to solve these problems. And hopefully one of these is looking for new techniques to find signals of interest from instruments that are producing a whole bunch of data. So as a means of introduction, my name is Adam Thompson, like Jim mentioned, and I lead our team at NVIDIA with building software and hardware platforms to intersect high-performance compute and AI with fast sensors. And a lot of times you'll see in the community that you have people build these big instruments and big sensors like radio telescopes, like we're going to talk about today, but also X-ray light sources, software-defined radios, and you name it. And so you have a detector team that has like a whole bunch of hardware experience and FPGAs and really amazing work, but the programming of that tends to be at a kind of a challenging level, right? Like it's VHDL and Verilog instead of something like Python. And then on the other side, you have the data scientists and the researchers who are consuming this data and trying to make valuable insights of what this is. So we're going to show some work that we've done in radio astronomy, but one of the broad takeaways here is what we're trying to do is build a generic hardware and software platform so that we can unite these data scientists on one side and researchers with the people who are making sensors. So this means we're trying to put compute closer towards where data is digitized and originates, so that way we can be more flexible, right? So in a lot of these instruments, you are doing measurements, you're doing a whole bunch of like gnarly signal processing at the front end, and then you write to a disk, right? And then we come in with like really fancy Python packages to handle this weird data that was collected in weird ways off of our instrument. So again, trying to unite these ecosystems together. And Luigi is a staff engineer at the SETI Institute and is responsible for creating a new GPU-based digital backend for radio astronomy. And our friendship and our collaboration has had a rich history within the SciPy community. We both presented last year and we presented this slide, and I wanted to like update it with 2025. But this all started with the creation of a software library called QSignal. So I created QSignal, and it was meant to be a GPU-accelerated version of SciPy Signal back in 2019. Gave a 2020 talk, which was, virtual for the first time, so recorded it in my basement. And then Luigi and I met, and Luigi created some really amazing visualization tools for high bandwidth streaming data for RF radio frequency sources. And then he gave a SciPy talk in 2022. And I was joking that we're only doing like these SciPy talks every 2 years, right, apparently. But anyway, through this, we now have had a place where we have tooling to do fast signal processing, but now we need a solution to connect to instruments. So one of the SDKs that I lead at NVIDIA is called Holoscan. And this isn't a talk necessarily about Holoscan, but one thing that it's doing is it's solving the I/O bottleneck when you go from sensors to GPU compute. So it's trying to say, okay, we have all of this data that's coming from the outside world. We are assuming it's coming in as an Ethernet packet, and we want to do a direct memory access from our NIC on our server to our GPU. So this reduces latency and increases bandwidth as you do this. And for these really high-speed instruments, this has been a critical part of unblocking some of these applications and moving compute closer towards where data originates. So QSignal ended up being fully merged into QPy, and then this year, and what this talk is about, is the creation of a new GPU-based digital backend for technosignature searches. So this is looking for, with the SETI Institute, you're looking for signs of extraterrestrial intelligence, but there's also the big science objectives of looking for fast radio bursts, looking for new pulsars, and other cosmic activity. So I want to start with our highlight. And if you had missed Chris Lamb's keynote or had a food coma or something and missed this, our breakthrough, and this was from earlier this year, this is about February or March time frame, is that we had built this signal processing pipeline that brought in 100 gigabits per second of data from the Allen Telescope Array in Northern California. So this was a real science experiment on a real instrument. And this was bringing it to a single NIC and GPU pair. So this wasn't the full bandwidth of the instrument, right? We were looking at essentially 96 megahertz from a whole bunch of antennas that were coming together. And we were able to get that data from upstream FPGAs straight into GPUs with a DMA. We used some of Luigi's GPU accelerated signal processing tools for beamforming and channelization. And then we used an AI inferencing model. So this was a model that we trained for fast radio bursts, which we'll get into in a little bit. And we pointed the telescope at the Crab Nebula. And with our AI, so we didn't have dedispersion, we didn't have matched filters. This was straight RF, beamformed RF data that went to an AI model. We were able to detect the Pulsar, I think Bates star, from the Crab Nebula, which confirmed that this was a valid approach to doing this. So we have a publication in review at Astronomy and Astrophysics, but what this looks like in practice, and Luigi made this visualization, if I can get it to go. And essentially this is all simulated data, but one can imagine this is the actual neural network running on this amount of data rate in real time. So you can see these little vertical, these diagonal lines that you're trying to look for, and these are detecting the signatures. Right, so we're looking for really narrow band signals of interest that are slanted as you look at your spectrogram. So it's drifting in frequency with respect to time. And the reason these are interesting is because the Earth is rotating. You're looking at Doppler. And so if you get a straight up and down line, that's probably coming from the Earth, right? Because it's very unlikely that a signal that you're interested in is going to have the same Doppler frequency as your own. So if we look at this, double clicking on the digital back end, this also compares the way that we were doing signal processing at the Allen Telescope Array previously, and then what we're doing now. And so previously, you had all of these antennas that fed into an analog cluster. So this was analog data. You get digitized on a bunch of FPGAs. There's some coarse signal processing that's going on with the FPGAs. And then you have a packetization step on those RF SoCs that essentially the output of this analog cluster are UDP packets, so Ethernet packets. So the original cluster essentially went from Ethernet data on FPGAs to CPU, where you did some CPU-based packet processing. You then had data movement to GPU for GPU signal processing, and then you move that data back to CPU and then for storage into memory. And so what we did was we used something called the Advanced Network Operator with Holoscan. We'll get to, again, we'll double click on what that is here in a little bit. But this was essentially implementing GPU direct RDMA and all of these packet processing libraries for low latency signal processing and networking underneath the hood. So it gave scientists, people like Luigi, a YAML file to write this. And if you've looked at people dealing with and spoken to people dealing with really large instruments trying to do this thing is an absolute pain in the butt, right? Doing it manually, and because you have you're looking at a Venn diagram of people who understand GPUs, people who understand networking, and looking at all of this, it's 40 people. And so anyway, this was really just trying to say, let's plug in our instrument and we're good to go. And so essentially this pipeline was architected in Holoscan. And so again, you're kind of eliminating some CPU overhead and CPU resources in here as well. And you're able to expand on these pipelines by just essentially adding a new node to your graph to do new compute. And so this is kind of the culmination of our GPU-based digital backend, and it is growing within the radio astronomy community and other communities as well. You saw Seher's great nanoscale imaging with NSLS2, and they're doing something similar with Holoscan. But to this point, the back end is expanding beyond just the Allen Telescope Array, so there are deployments at Astron, at the Westerbork Radio Observatory for a billion-star search. It's an all-sky, all-the-time search. The French SKA Pathfinder Nénuphar is also doing an FRB detection pipeline, and then the Indian GMRT, which is another fast radio burst and pulsar detection instrument there. So we're going to talk a little bit about how we did it and how you can too. And one of the things I want to focus on is that when we're talking about signal processing and detection theory, it's a community that's, I would say, to be totally honest, like a little hesitant for looking at AI for some of these detectors. And you have to answer this question: okay, is this different, or is it new and valuable? Like, is this interesting because it's different, or is it interesting because it's actually adding something to science? And so the first publication that at least I was aware of that we were involved with came from Jerry Zhang, and essentially this was looking at recordings from the Green Bank Radio Observatory in West Virginia, and he had implemented a relatively simple at the time, I think this was around 2017, convolutional neural network to look at spectrograms. And from this study, he found 72 previously undiscovered fast radio bursts, right? And so one of my jokes is like, we could have very well found ET at some point, but it's just sitting on some hard drive somewhere, and we just didn't have the tools to actually see it. So this was showing that, at least in this instance, the AI tools were actually finding things that conventional metrics had missed. And so kind of the next iteration was, instead of a convolutional neural network, Peter Ma, who is our collaborator for this work as well, did an autoencoder approach and found even more technosignatures from a wide number of stars, and this was published in Nature Astronomy Journal. And then we have a paper that's in review, and I used AI to generate this. You can probably tell because no radio telescope would look like that. It's a terrible radio telescope to build that. But this is our real-time end-to-end deep learning algorithm for FRB's detection. And this is a ResNet-based model that Luigi will talk about more here in a second. But the kind of the value here is you're taking these offline algorithms and we're putting it online, right? So it's putting it as you're collecting data from the instrument. So I'm going to turn it over to Luigi to talk more about how we generated this model, how we did synthetic data generation, how we trained it, and then some choices of the model architecture.
So first thing is the FRBNM, the model that we use to detect the pulsar in real time. So we had to do some design choices when we're designing this model in particular. The first one being that it needs to be very lightweight, because we are getting input from the telescope, the ATA, that is around 1.5 terabits per second. So even with integrating that data and making summing that data to later do the inference, you really want this to perform less than let's say 16 milliseconds on each spectrogram, and a spectrogram being a 2D image, for example. So our goal was to reach less than 100 megabytes of the model and reach 99.99% of false of accuracy. So, and we kind of did it. The final model has 82 megabytes, and it's based on the ResNet. So no transformers here. So it's a very efficient way that TensorRT can get this model and run the inference with our new pipeline that runs on Holoscan. All the data that we trained this model was created via augmentation. So we got the recordings from the Allen Telescope Array, and then interposed a simulated drifting signal, that is the FRB, the pulse, and then we trained over that data. So the data set contained 300 gigabytes of data, more than 200,000 bursts. And in the end, we got very, very good results from this tiny model in a way that we can receive the data, compute it to the GSP that we usually do, run this, pass to this model. This model will tell us if the data is relevant or not to the observations. And we can choose to keep the data or discard the data, so you don't need to require the 1.5 terabytes to disk. And currently, it's in review, as Adam said, and expecting the next month or so on astronomy and physics. This is more like if you're concerned about like the details about the neural network that we used. Again, a very basic ResNet model here. And now Adam to talk about the deployment.
Yeah, and one thing, backing up for a second, one thing is the kind of state of the art for AI techniques was the Spandeck CNN, and we've shown, and this will be more in the paper, about a 500x speed up, over that as well. In terms of deployment, just in general, and this is a bigger, kind of a bigger conversation than even just radio astronomy, is, and I mentioned this at the beginning, was really trying to push more of the compute closer towards the data converter, right? And again, this is about unifying the ecosystem of people developing. So in these traditional like data acquisition or DAC-based architectures, you have a data converter, which is digitizing data, it typically sends that data to an FPGA, which is doing low latency signal processing, low latency triggering, right? So like order nanosecond decisions of do you keep or do you discard observations. And then like precise timing and I/O. So FPGAs here are often like doing packetization, just like the RF-SOC before, to get something that's like a little bit more consumable by the downstream system. So then we have a NIC, and then a CPU, and then you have like 10 seconds of circular RAM for buffering for doing processing. So this is a great hardware-defined ecosystem that ensures ultra-low latency. Well, one of the things is it's really challenging for, as I mentioned before, it's really challenging for someone who wants to program in like Python or CuPy or JAX or whatever to like be anywhere above, like that line, and I should have put a line in there. And what we're really trying to do is to develop what we would call a science programmable edge, where essentially what we're doing here is we still have an FPGA because you still need FPGA for ultra low latency, particularly if you're doing, high energy physics with those ultra low latency requirements. But the thing is this FPGA can be a lot smaller, right? Like you're not buying like a huge FPGA to do a bunch of signal processing. You're now buying a smaller FPGA to do your ultra low latency work, and then you have a GPU direct memory access between this FPGA and GPU via a NIC, and then you can move the signal processing that you previously had on your FPGA to your GPU, and you can use libraries, at will. Like I know, like CuPy you have the old QSignal stuff in CuPy, and there's a ton of other libraries that have signal processing functions in there as well. The other component here is, again, trying to make this pipeline so that you don't have a CPU in a critical path. And there's often a need to do archiving and storage, right? Like we're talking about a lot of online processing. We still need to like save things for like obvious reasons. So we're implementing GPU direct storage, right? Which is like GPU direct RDMA, but you're writing to NVMe. And one of the core enablers here is this green box, which again is the direct memory access between NIC and GPU. And just really quickly, this is the more detail on Holoscan's advanced network operator. And the big thing, there's a lot of detail here. There's a tutorial that you can scan up there that goes through all of the delineations between different packet processing backends and trade-offs of what they are. But again, the big goal here is how do you just plug your sensor into your GPU without doing a whole bunch of coding. So I'm going to turn it back over to Luigi, and he's going to talk about more of the GPU backend.
So to talk more about the next generation digital signal processing that we are developing, so we chose to integrate everything to a single package. So you can, if you have a telescope and want to integrate like what the work that we did on like all the GPU accelerated package ingester or the DSP that does the beamforming or channelization, you can with this package here. So everything is set up for you to do whatever you want from it. From the three aspects of processing that I always tell, it's like acquisition, UDP, sorting. Then we need to do some kind of DSP, so beamforming, correlation. And then after you're done with doing all your transformations, you need to write to disk. And then you want like RDMA directly to disk, etc. So Stellene, if you got the name, come talk to me later. It's amalgamation of all these technologies with Holoscan that we are currently employing. So, and it's available like MIT licensed and on already open source. The development is going through like completely publicly. And as Adam mentioned, the aims to replace the CPU-based one. Another thing that I already spoke for is Blade. That is our breakthrough listen accelerated DSP engine, Blade Runner reference. And you can, this one is basically for astronomers that you don't need to rewrite your beamformer for the 100th time, so you can use Blade to do that for you. Other than this, like there's kurtosis to eliminate RFI from your data. And other things. There is a Python interface that you can use to, if you want to write a module for Blade, you can use the Python interface to test it. That's how we test it. We write one algorithm that's very slow with NumPy, and then we test against the output from Blade. Blade is always like 100 times faster, but that way we check that is correct, the output. And after you did everything, you have your telescope, you have your data processing pipeline, and you want a way to visualize that data, you can use SciPy that is like multi-platform, hardware-accelerated visualization tools. It's flow graph-based. Not sure if you guys are familiar with GNU Radio, but it's almost the same idea. It's a flow graph-based. You have the acquisition like a file reader, and then you go to a waterfall plot or a spectrogram. You can use SciPy for this. And SciPy has heterogeneous support, so you can run that on CUDA, on Metal. It even run on iOS, so iPhone, iPads, Apple TVs, whatever. And also, there's a Python interface for this that I heavily inspired on Matplotlib, and it's more focused on performance. So you can generate one matrix every 10 milliseconds, feed to this thing, and it will show in the screen at 60 FPS, like unlike Matplotlib most of the cases. And like very simple API. Adam, to talk about the future work.
So one of the things that we've seen for emerging workloads of data acquisition, and this is, there might be a more like academic term for this, but we call it little model, big model. So Luigi mentioned that, you know, for doing like the real time, like you have sensor data that's coming off your instrument, you need something lightweight, right, just to keep up with like the data flow that's here. But then we can also have this little model, which is essentially triggering, like we found something interesting, which triggers something that we do in radio astronomy all the time, is you're looking at like a longer integration window, right? So it's kind of a near real time, but you'd be able to do a more, a heavier weight AI model, or just like heavier weight signal processing to get a better idea of what's going on. But you're kind of tipped and cued based off of what this lightweight inferencing step did at the beginning. So that's the bulk of our presentation. We do want to give a shout out to the SETI Institute. They're really amazing collaborators, and they're almost always hiring. And so it's not just astronomers, it's electrical engineers, biologists, all different types of folks. And the mission is looking for some of the biggest challenges of humanity is understanding, are we alone? And then also on the NVIDIA side, we have a series of tutorials for you all to use, and I think there's a free class with this QR code. So thanks again for your time. Really appreciate it.
Does this work? Yeah. Oh, cool. All right, so first question. Your model is designed to find FRBs. What about finding weird stuff? Are there plans to build an anomaly detector for this architecture, something you don't have a labeled data set?
Yeah, so we are thinking about developing a framework that anything that you would like to find in our terabits of data can be like integrated. So if you want to create a model that finds squiggly lines in the shape of like S-shaped squiggly lines, you can train the model to do that, and you can run in real time, and it would give a result if it is a S-shaped squiggly line or not, or whatever the hell you want. It is made to be very modular. So if there's a research for a very specific thing, you can retrain the model and deploy that.
Okay. I see there's another question coming in, but while it's coming in, I could ask a follow-up for that. You were talking about allow list type signals, looking for a weird squiggle, particular F shape or something like that. But what about deny list, like everything except the stuff we know?
Mm-hmm. Yeah, that also probably it's very modular, very you're free to do whatever you want. So if it's not a match, just ignore it, or if it is a match, ignore it. If you can train a ResNet to do something that you want, you can deploy it here. It's very flexible.
Okay. Next question is, are there plans to make this adaptable to other types of telescopes? Radio astronomy has a different set of data processing than, say, telescopes in the visible.
So algorithms for imaging telescopes are different than the radio telescope for the most part, but there is nothing. You can integrate your algorithms within the Stellene project and get resources like file writer and the network ingestion tools. And we also use like HDF5 writing the files to disk using GDS, GPU's direct storage. So that's also very useful for imaging, for example, or other telescopes.
Yeah, and I'll add that one of the goals is to, if you are looking for a new signal, you shouldn't have to completely re-architect your data pipeline, right? So one of the things that we were trying to do, and this is also specific to Holoscan, is that if you can provide like a general platform that other folks can build on top of that can easily handle I/O, and then you have that I/O, no matter what it is, no matter what that data is, whether it's optical data or radio frequency, like voltage samples, time, pressure, whatever, that you can essentially tap into that data that's coming into your GPU, and then you can use like the power of some of these CUDA-Python tools on it, right? So it shouldn't matter what it is. And I think some of the flexibility, even of looking for things other than squiggly lines, is that your change to your pipeline should be, I just point to a different AI model than before.
And everything like Stellene being written in Holoscan, like if you have another Holoscan, another group that made a Holoscan operator that processed the data in a way that you want, you just integrate with the Stellene and other operators on our side. So like the sky's the limit, Holoscan serves like a generic way to pass data through elements. So it also facilitates the go.
Okay. So there's another question. With RDMA, you have to parse packets on the GPU. That sounds hard. Did it force you to wire format the change?
So what we've done, and this is some of the magic that's abstracted away in the packet processing libraries, like the back ends. So for something like DPDK, you're essentially passing pointers. And so essentially what you're doing is the NIC is responsible for flow control. And so what it can do is that you can essentially say, I'm going to do what's called a header data split. So you can read the first n number of bytes, which is in your YAML of saying this is my header, and then the remaining number of bytes in your packet get moved to essentially a circular ring buffer in GPU memory. So you still have like your CPU that's doing, like pulling the NIC for new packets. So the CPU is in the mix here, but you're essentially just filling up a circular ring buffer on the GPU. And again, like your exposure to it via the advanced network operator is with like just some configuration steps. So Luigi was able, and Luigi isn't a network programmer, he got the advanced network operator up and running in 15 minutes at the outset. So, and you had to change something about the metadata for it too, and it was pretty quick.
Okay. All right, thanks. Any other questions? Want to give you a last chance?